All right, welcome to another lecture in the course. We're looking at transforms, Laplace transforms of derivatives and how to use them to solve differential equations. This is still section 6.2 in the book, and you can get the book at this URL. It's also linked in the description. You can browse the book for free online, or you can get a PDF, or you can get an inexpensive paperback there. All right, so let's go look at more differential equations with Laplace transform. So, so suppose that I have this differential equation and I'm writing it in sort of more shorthand notation. I'm sort of hiding the left-hand side here under this in this operator notation. So, for example, if this was just a simple mass spring setup, it might be something like x double prime plus x or something like that, right? So that's what's on the left hand side over here. So that's this linear differential operator. And on the right hand side, that's the input. So really, we're thinking of f as the input and x as the output, right? So if I have some circuit, f is sort of the input. I'm looking at what I'm doing with the voltage, let's say, and x is the output. It's what's happening in the circuit itself, right? How's the current running through the circuit, right? So, and what we want maybe is so we have one circuit, and we want to figure out how does it respond to different inputs, right? As the circuit is this device, and I want to know what's going to happen if I put all sorts of different inputs into it. So Laplace is actually very good at figuring that out, to analyzing this sort of this sort of problem. And when we're going to do this, let's just consider all initial conditions 0. So, suppose that the circuit is at rest, basically. Really, because the initial conditions, as we saw, except in the sort of the idealized case, it never happens. They will go away. You only have what's happening sort of long term anyway. So you can sort of ignore the initial conditions. Let's just set them to 0, right? So there's just this transient part, and it will go away. So let's just ignore it. Let's set the initial conditions to 0, because that makes the analysis easier. So if we take the Laplace transform of this guy, what will happen is that the left-hand side will always transform to some function times the transform of x, right? And the right-hand side, well, it's just whatever the right-hand side transforms to. So capital F, right? Now the ratio, if I look at, if I divide, x divided by f, which is the same thing as 1 over a, right? So if you divide it by f, divide by a, right, you get this equation. That ratio is called the transfer function, and that's denoted by h of s. It's really just 1 over a, or it's x of s over f of s, right? Now, the solution then can be written as, well, we have our output, at least its Laplace transform, x, is really just the transfer function times the input, or the Laplace transform of the input, right? It's just this very simple equation, right? And we can, now we could just produce, once we know h, we can just produce outputs for inputs, right? We don't have to do anything, anymore, right? We just sort of, we can just, at least Laplace transforms off, right? So in the Laplace, in the s variable, right? In the Laplace transform land, we can just, churn out outputs for whatever input we dream up, right? So it's just a multiplication by the transfer function. Now, moreover, to figure out h, it's this ratio, we really only need to know the output for one input, right? So if you have an you know you send an input into your into your device, into your circuit, you figure out what the output is. You have the transfer function, right? Now, if you notice even more, you don't really even need to know the L itself, right? As long as well, as long as you can get the Laplace transforms of the input and the output, you don't need to know what L is. So you don't need to know the exact parameters of the circuit, right? Or of the mass spring or whatever device that you're analyzing. You just need to know one output for one input. And once you know one output for one input, you can find all outputs for all inputs, right? And you didn't need to even know what this L is, right? So you can get this sort of by experiment, right? You can get, you can see how does the input behave for some. So how does the device, your circuit, behave for one input? You get the output, and you get the transfer function, and you're good. All right, let's see this on an example. Let's suppose that it's an example where I know this is the L, that's the L of x, right? So, and we're assuming zero initial conditions, right? So the Laplace transform of the equation just becomes this. And well, if we look at what is, I basically just write this well, I guess divide by f, and then factor out the x and divide by the s squared plus omega naught squared, just to find this ratio. That's what we're solving for, right? We get this thing. So that's the transfer function. It's 1 over s squared plus omega naught squared, right? Where omega naught squared is this constant over here, right? So if the input is just the constant 1, that means 1 over s in the land of Laplace transforms. Then the output is this thing, right? It's the transfer function times 1 over s, right? That's going to be the output. So once I know this transfer function, I can generate outputs, right? I know what the outputs are. In this case, the inverse Laplace transform gives this thing, but the point here is this formula, right? Now, for any other input, again, it's just going to be, I just write down what this thing is, right? That's going to be the Laplace transform of the output, right? I just multiply the Laplace transform of the input by 1 over s squared plus omega naught squared. All right. So that's transfer functions, and we're gonna see this coming up more in the next few lectures. Now, let's change gears a little bit, but not really, because Laplace deals with derivatives easily. If you just think about it, it can also deal with integrals. I mean, it's really the it's really the same thing, right? So if if you use a little bit of calculus, you will figure out this property, that if the Laplace transform of this integral, and here notice that this is a definite integral. I need something specific. I don't want an indefinite integral. I want a definite integral, but this is the antiderivative of f. It's just the antiderivative of f that's 0 when t is 0, right? That's what this integral gives me. And so if I take the Laplace transform of that particular antiderivative of f, it's really, I'm just dividing by s, right? So differentiation in the t variable was multiplication by s. So integration is division by s, right? And we just have to look at this very specific antiderivative so that we don't have that extra term, right? That was the initial condition or whatever here. So here we're basically setting the initial condition or that the value of that antiderivative, we're setting it to 0, right? So that's why it doesn't appear there, right? So this is another way of thinking about it, right? Is that it's if I do inverse Laplace transform of 1 over s times capital F, then it's just the integral from 0 to t of little f of t, right? The inverse Laplace transform of f, capital F, right? Now, maybe, yeah, just just a note about these tau's, right? Obviously, I can't use t over here, right? Because I'm using t over here. So I just need some dummy variable, right? So the tau is a dummy variable. I can't use s, right? Because s is our variable. I can't use u, like from calculus. Yeah, okay. So we just need to come up with another letter, right? There's nothing special about tau, right? It's just that was an available letter. That's all. And it's just not t, right? It's a different letter from t. It's a Greek t, right? All right. So let's do an example. This is actually something that we saw before, and I told you to solve this problem with partial fractions, but we could actually use this formula, right? So if I think of this as 1 over s times this guy, well, here I have the capital F is this 1 over s squared plus 1, and I'm multiplying by 1 over s. So really, I'm just integrating from 0 to t the inverse Laplace transform of 1 over s squared plus 1. And that's just sine, right? So if I integrate from 0 to t sine of tau, right, I will get, well, 1 minus cosine of t. That's precisely what we got before, right? Or what you got before in the exercise, right? That was an exercise. Okay. Now, this is useful. Well, one place where it's useful. I mean, you can do inverse Laplace transforms, for example, with it. But we can also solve some other equations, what's called integral equations, which is just an equation where an integral appears instead of a derivative, right? So a differential equation is one where derivatives appear. Integral equation is one where integrals appear. Right. So, for example, a very simple one could be this thing, right? And I can solve this algebraically, and I can just integrate because this x appears sort of, once without and once with the integral, right? Just like a differential equation, but now I have the integral rather than the derivative, right? Okay, so let's apply the Laplace transform. It's like before, but Laplace transform both sides, and we know how to Laplace transform both sides over here, right? And we remember that the Laplace transform of something like this is given by this formula. So Laplace transform on the left is just capital X minus 1 over s squared. That's just the Laplace transform of minus t. And the Laplace transform of this guy is 1 over s times the Laplace transform of x, right? Now, this I can solve, right? I get, x is 1 over s times s minus 1. I do partial fractions to get this thing, and so now I can do inverse Laplace transform just using the table, and I get e to the t minus 1. And you could take this and plug it into here to double check that we really did solve the equation, right? And if I plug in this formula over here, at the left-hand side equals to right-hand side. All right. So let's change gears a little bit again. One type of input that appears that appears quite often, right? It's also a periodic function, right? I have, you've already seen like sines and cosines, but it could be more complicated. It could be, it could be something that's defined piecewise, let's say, right? So how do we deal with periodic function, or how does the Laplace transform deal with periodic functions? And it's actually fairly simple. At least the forward, the backwards is a little bit more complicated, and we're going to skip that. And again, you would use some sort of a table. Anyway, so let's see what happens if I have a periodic function. So it's a function where f of t is equal to f of t plus p. So p is the period, right? So whenever I move p in the time direction, the function is the same, right? So for example, sine is 2 pi periodic, right? So sine of t is sine of t plus 2 pi, right? Okay, so we have this identity, right? If the f is periodic, right? P periodic, right? So, well, what's the Laplace transform of f? It's just what this is, right? Let's split this integral up into two pieces. I mean, it's just an integral, so we can compute it from 0 to p and from p to infinity, right? So let's leave the first part alone. Let's see the second guy, right? So what we're doing is we're taking this and we're making it into this. That's just a change of variables, right? That's a u substitution, right? So we want to go, instead of from p to infinity, we want to go from 0 to infinity. All right. But now this f of t plus p, right? That's just f of t, right? Moreover, this, over here, I really have, this is really a product of two things. E to the minus st times e to the minus sp, right? Now, p and s are, as far as the integral is concerned, they're constant. So I can pull that out. So what we get is this. So the first term didn't really change. That's just this integral from 0 to p. But the second term became this. Now, you will notice that this thing, well, that's just the Laplace transform, right? So that's just capital F, right? So you solve for capital F, and you get this this formula, right? And it makes sense that I only need to do this integral for from 0 to p, right? Because once I know my function from 0 to p, I know the function everywhere, right? So I only need to do this integral over a finite interval, and I get the Laplace transform. All right. So let's do an example. Let's suppose it's a sawtooth. It's this function that is it's periodic. I'm going to make it a 1 periodic, and it's going to be t on the interval 0 to 1, and then it's going to be 1 periodic. So we're going to assume this. So it looks like this. It's t over here, but then to make it periodic, it has to be sort of the same if I add 1, right? So it's actually t minus 1 on the interval from 1 to 2, and t minus 2 on the interval from 2 to 3, and so on, right? So that makes it periodic, right? So it looks like this, if you think of sort of vertical lines where the jumps are, it looks like a sawtooth, hence the name, right? So how would we compute this? Well, p is 1 because that's the thing over here. That's the period, and so I plug that in, right? So I have 1 over 1 minus e to the minus s, and the integral of the function f over the interval 0, 1, and on 0, 1 the function is just t, right? So that's why we have t here, right? All right. Well, we do the you do the do the calculus. So you have to do integration by parts, but yeah, that's what it will come out to, right? It comes out to this, and you can simplify a little bit to get this, but it's relevant. That's what it is, right? So again, you see that it's actually rather simple how you find Laplace transforms of periodic functions, right? So the Laplace transform can handle all sorts of functions, right? Even ones that have sort of ugly definitions, right? I mean, the sawtooth is, I mean, it's not a nice definition uh, uh, in terms of, like nice formula, right? It's not even easy to write it with Heaviside function in a really nice way. But the Laplace transform is really easy, right? So Laplace transform handles those functions really well. Okay, so next time, what we're gonna do is we're gonna look at how Laplace transform deals with multiplication, and multiplication on the Laplace transform side, so in the S variable. And because it's not the Laplace transform of multiplication in the T variable, right? That doesn't work that way. But so we get convolution. So that's what we're gonna do next time. All right. So see you then.